Okay, I think it's time to start. We are still working on the construction of the molecular orbital diagram of a square planar complex, including pi bonding. And in the last class, we have determined which orbitals that you can combine to form molecular orbitals from the standpoint of symmetry. So now let's use that knowledge and construct the actual molecular orbital diagram. So you see here, on the left-hand side, again, the metal orbitals, the 5d orbitals, the 4s orbital, and the 3,4p orbitals. And see here also, in addition, all the symmetry types associated with them. So now on the right-hand side of the molecular orbital diagram, we now need to consider the sigma ligand group orbitals. So these are the ligand group orbitals for sigma bonding, and their symmetry types, A1G, EU, and B1G in this case. But in addition to that, we now need to consider the pi ligand group orbitals. And in addition to that, we need to consider the pi star ligand group orbitals. Now again, which of these two we use would depend on whether our ligand acts as a pi acceptor or as a pi donor. So in our example of the nickel tetracyano complex, tetracyano-nickel complex, the cyanoligand acts pi donor and not as a pi acceptor. We can see this from the fact that the pi star ligand group orbitals are energetically far higher than the metal d orbital, whereas the pi ligand group orbitals are energetically very similar to the metal d orbitals. So therefore, in good approximation, we can consider these orbitals here as non-bonding, and interactions will be primarily between the bonding pi ligand group orbitals and the metal orbitals. So let us go through the symmetry types step by step, and let's construct the molecular orbitals of these different symmetry types. So for instance, we can start with the A1G symmetry type. You see that there's the 4s orbital, which has that symmetry type. There's this 3d orbital, which has that symmetry type. And in addition, we have that sigma LGO, which has that symmetry type. So this is actually something we already previously considered when we constructed the molecular orbital diagram, considering the sigma bonding only. So what is the result? The result is that we have one bonding molecular orbital, one approximately non-bonding one, and one interbonding one. We label these 1A1G, 2A1G, 3A1G, respectively. So pi bonding is not involved with respect to this symmetry type. So now let us consider next the B2G symmetry type. So one metal d orbital has that symmetry type, and there's also one pi ligand group orbital that has that symmetry type. So that means that we will create one bonding molecular orbital and an interbonding molecular orbital in addition. Now, of course, there's also here an additional B2G, but it's energetically very high, so that this remains pretty much non-bonded. We can nonetheless write it into our molecular orbital diagram. All right, so we can, for instance, choose next the B1G symmetry type. You see one d orbital has that symmetry type, and one of the sigma ligand group orbitals has that symmetry type. So pi bonding is not associated with that symmetry type. And we would have here this bonding molecular orbital, the 1B1G, and here the interbonding molecular orbital 2B1G. Okay, now what is next? Well, we can, for instance, choose the EG orbitals next. So you see that the EG orbitals have a bonding partner with the pi ligand group orbitals. So formally, without considering pi bonding, they remain non-bonding, but now they are actively involved in the bonding. And we can say that, well, we would expect a bonding pair of double degenerated molecular orbitals with that symmetry type and an interbonding pair of the same symmetry type. In addition, of course, there are also these EG orbitals here, but they again remain largely non-bonding because they are energetically too far away. Okay, what else is to consider? Well, we have also EU orbitals. So the 4p orbitals are EU type, at least two of them, namely the px and the py. So we have now EU orbitals in the sigma ligand group orbitals and EU orbitals among the pi ligand group orbitals. So that means that the EU type molecular orbitals are influenced both by sigma and pi bonding interactions. So we have overall 1, 2, 3 pairs. So that would mean that we get 3 pairs of molecular orbitals of EU type. We can approximate that one pair will be bonding, another pair will be interbonding, and the third one will be energetically in the middle and will be approximately non-bonding, could also be slightly bonding or interbonding, but not strongly bonding or interbonding. You would not expect that. So what else is left? Well, we still have the A2U symmetry type to consider. Okay, so the 4p orbital is of A2U. And we have also one A2U orbital among the pi ligand group orbitals. So this will give one bonding molecular orbital of A2U symmetry type and an interbonding molecular orbital of A2U symmetry type. Okay, is there anything we have not considered yet? The answer is, well, we have this A2G pi ligand group orbital. So this one doesn't find a bonding partner because there's no A2U metal orbital. So this one will remain non-bonding. And this A2G will remain non-bonding as well. So is there anything else? Have we another symmetry type? Yes, there's one more, which is actually the B2U here. So the B2U pi ligand group orbitals also remain non-bonding because no metal orbital is of the same symmetry type. So we can write the B2U is non-bonding into the molecular orbital diagram, and the same is of course true for this pi star ligand group orbital, which also remains non-bonding. Okay, now we are really finished, and you see that our molecular orbital diagram now looks quite complicated. And if we first saw it, we may have been just overwhelmed by it, but you see, you can relatively easily construct it by systematic combination of atomic orbitals of the same type. So one step is left to do, of course. We have to fill in the electrons. Okay, so now our sigma ligand group orbitals are being full. Our pi bonding ligand group orbitals are full. These ligand group orbitals, because of interbonding nature, are empty. So in addition to that, if this metal here is a nickel 2+, we have a D8 ion, and we have 8 electrons in the metal d orbitals. So how many electrons do we have overall? Well, that's 8. So that's another 8, that gives 16. And that here is another 8, which gives 24. And here we have another 8, which gives overall 32 electrons that we have to fill now according to energy into the ligand group and into the molecular orbitals. Okay, so now let's just do this. So these ones here, for the sigma bonding, we can fill first into these bonding molecular orbitals. So we saw these electrons previously already when we considered only sigma bonding, but now in addition we can fill the pi electrons here into the molecular orbit with the next higher energy. Okay, so these one we can call the sigma bonding molecular orbitals. All right, so that fills this one, that fills this one, that fills this one. So we have spent 6 of the overall 8. Okay, then this one, then we have spent 8. Now we have 10. Now we have 12. Now we have 14. And now we have 60. Okay, we see that not all pi orbitals have been stabilized, namely the A to G and the B to U, but some of the pi electrons have been stabilized because of the pi interactions. So we would understand why the pi interactions are stabilizing the overall molecule. Okay, and we can therefore say that these molecular orbitals are the pi bonding molecular orbitals. So now what electrons are left? Well, we still have the d electrons to consider. We see that we have 8 d electrons here. Okay. So we have to fill these 8 electrons now into the orbitals of next higher energy. So that fills this B to G, that 2Eg, and the 2A1G. Okay. So this makes the 2A1G the highest occupied molecular orbital. So you see that the pi interactions slightly destabilize the d electrons, but overall we have a net stabilization of electrons because of the stabilization of most of the ligand electrons. However, these 8 orbitals are not greatly destabilized because all the orbitals are not strongly interbonding. They're either weakly, either approximately non-bonding or weakly interbonding. Okay, so now we can again say that, well, these orbitals here, they are the metal d orbitals in the square planar crystal field. Okay, and they split up in energy according to the square planar Ligand field. So you see that the D8 electron configuration is actually ideal for the square planar geometry because we have 16 electrons, valence electrons, only according to our electron counting method. If we had 18, we would actually have, we would have to fill this orbital here, this 2A1U in addition, and this 2A1U orbital has a much higher energy than the 2A1G. Okay, so this also explains why there's an exception from the 18 electron rule. So note again that when we count electrons according to the neutral atom method or the oxidation state method, that we only consider sigma bonding and not pi bonding. Okay, that means that we would only consider these electrons here, the sigma electrons coming from the metal, and these sigma electrons coming from the ligand, which are 8, and these 8 electrons in addition coming from the metal. And these 8 plus these 8, that give 16. Okay, if you had more metal d electrons, as I said before, we would have to fill these into this molecular orbital here, which is much higher in energy and would be energetically much less favorable. So we can say that our ligand field theory can explain the exception from the 18 electron rule and can explain why square planar complexes like the 16 electron configuration better than the 18 electron configuration. Okay, now we are finished with ligand field theory. So before we move over to the next chapter, I would like to ask if there are any questions. So are there any questions at the moment? Okay, so this does not seem to be the case. So therefore, I will move on to the next presentation, which will now start a new chapter, still related to the previous chapter, and which will be about the electronic spectra of coordination compounds. I told you a number of times before that a good bonding theory should be able to explain the optical spectra of compounds well, and ligand field theory, of course, can explain optical spectra through electron transitions, but we will see that the picture that ligand field theory provides is still too simple in order to explain many electronic spectra. So we have to make additional consideration in order to explain electronic spectra really satisfactorily. So for instance, there's an octahedral complex known such as the hexa, aqua, nickel 2+. Okay. And in this complex, the nickel has the D8 electron configuration. Okay, so that means, according to the ligand field theory, our frontier orbitals would be the T2G orbitals and the EG orbital in the octahedral Lagrange field, and we would have delta O in between the T2G and the EG orbitals, and there would be 8 electrons in these orbitals. So because of energetic argument, 6 of them would be in the T2G orbitals, the DXZ, the DYZ, and the DXZ, and 2 of them would be in the DZ square and the DX square minus Y square. So now, how could we explain absorption of visible light by this complex? Well, we could say that, well, visible light of the correct wavelength could promote 1 electron from a T2G to an EG orbital. Okay, so now how should our spectrum look like? Well, we would actually expect there's only 1 absorption band okay, because there's only one energy barrier that we need to cross in order to promote an electron from a T to G orbital into an EG orbital. So now we can compare this with the reality. Okay? And the reality is, unfortunately, much more complicated. So we would have at least 3 absorption bands present. Okay, so you see here this one, then this one, that's actually even 2 overlapping, and there's another one, and there could even be multiple bands overlapping underneath this band here. So it seems that there are many more electron transitions possible than on in this one, and that means that the electronic structure of our complex must be significantly more complicated than what ligand field theory would predict. Okay, so you see from that that there are still significant shortcomings of ligand field theory. So now the question is, what causes these shortcomings? And the answer to that is that ligand field theory does not assume any electron-electron interactions. So all orbitals that are being constructed are actually one electron functions, and they neglect the electrostatic interactions between the electrons in the orbitals. So ligand field theory only works on the basis of interference of orbitals due to the nature, due to the wave nature to form bonding and interbonding molecular orbitals, but it actually doesn't consider the electrostatic interactions and electron-electron repulsions between the electrons. So it assumes that all these electrons in these orbitals, basically, they are independent from each other and there are no interactions between them. So this is not realistic. So in practice, the electrons do interact with each other. And the question is now, how can we describe these interactions? So now let us first understand why these interactions are actually different for what is called different microstates. So you see actually here one possible microstate in which we have one electron, for instance, in the dxy, and the other electron in the dxz orbital. Okay, so now we can, for instance, promote the electron from the dxy into the dz square orbital. Okay, so that would create another microstate in which now one electron is in the dz square orbital and another electron is in the dxz orbital. Okay, however, we could realize this state of one electron being in the T2G and the other electron in the EG orbital also by another electron transition and another microstate. Okay, and you see this here, we again start out with one electron being in a XY and the other electron in an XZ, but now we promote the other electron from the XZ in the DZ square orbital. So ligand field theory would say, well, these two microstates here have the same energy. Okay, because it assumes that, well, the electron-electron interaction, there are no electron-electron interactions between these two electrons, or at least the electron-electron interactions would be all the same. But it's actually not plausible to assume that, considering that these orbitals have different shapes. Okay, So as I said before, these two microstates have different energies, and we can explain this simply by geometric arguments. We just want to qualitatively understand this. Okay, so we have here a dz square orbital interacting in this case with a dxz, while here we have the same dz square orbital interacting with a dxy. So you now see that, well, just because of geometric arguments, one would not assume the same kind of electron-electron repulsion for this case in comparison to that case, and thereby we would understand why these two different microstates belong to the same state would actually have the same, actually have different energies. Now that is a fairly qualitative explanation. So now let us go to a more quantitative explanation and develop a more quantitative approach. So we can approach the problem by asking ourselves, well, what would we need to do in order to explain our electronic spectra satisfactorily? Well, basically, we would need to know the energies of all the different microstates, okay, and then group all the microstates that have the same energy together. In such a group of microstates having the same energy is called a term. So if we just knew all the terms, okay, we would have knowledge about all the possible energy electron transitions between these terms, and that in turn would allow us to understand the electronic spectra. Okay, so now let us more quantitatively determine what determines the energy of a particular microstate. Okay, so let us first consider what is called the Russell-Saunders coupling of electrons in free ions. Okay, so we shall assume here that our ion is not yet coordinated by a ligand, in that we are only looking at an isolated metal ion. So Russell-Saunders coupling means the interaction of the angular momentum of the electrons. Okay, so the angular momentum of a single electron is defined by the quantum number ml. Okay, whereby ml can run between minus L and L. So for instance, if you have a d orbital, then, well, L is 2, right? And ml can therefore run between -2 and +2. That's why we have 5d orbitals. So now when we have multiple electrons, then the angular momentum of all the electrons just add up. And that gives, well, capital ML, which is called the total orbital angular momentum, now considering all, all electrons. Okay, so now the maximum capital ML value is called capital L. So this is a quantum number of significant importance. It's called the total angular orbital quantum number. So why is it important? Because it determines the number of microstates that belong to a certain term, and the orbital quantum number also gives information about the energy of a particular term. So the number of microstates in that particular term is given by this formula, just 2L plus 1. Okay? And that is because ml can vary between minus L and plus L. Okay. And in addition to that, we now need to consider the interaction between the magnetic momenta of the electrons due to the spin. Okay, we know that an electron has also quantum number ms that reflects the spinning of the electron around its own axis, and we can either have, well, a value of plus a half or minus a half. So ms equal to plus a half means spin up, while ms is equal to minus a half means spin down. Okay, so now when we have multiple electrons, again, the ms values of the individual electrons just add up to give capital ms. And now the maximum ms value is called capital S, and that's the total spin angular quantum number. So this total spin orbital quantum number is again important because it defines the number of additional microstates due to the spin. Okay, so the number of the microstates in the term due to spin is 2s plus 1. Okay, so now overall we have now microstates due to the interaction of the angular momentum of a single electron, but also we have interactions due to the spins, so that the overall number of microstates in the term is, well, 2L plus 1 times 2S plus 1. All right, so that now defines what is called the term symbol of a particular term. So the quantum number L determines, well, by which the letter associated with the term symbol. Okay, so if L is equal to 0, it's called an S term. If L is equal to 1, it's called a P term. If L is equal to 2, it's called a D term. If L is equal to 3, it's called an S term. You see that this nomenclature goes in analogy to the to what is used for orbitals. Okay, so like in an S orbital, well, L would have to be 0. In an S term, capital L has to be 0, and in a P term, like L would need to be 1. In a P term, capital L needs to be 1, and so forth. So then you place actually the spin, next you place actually spin multiplicity as a superscript to the left of the letter that defines L, and the spin multiplicity is nothing else but 2s plus 1, which is equal to the number of microstates due to the spin multiplicity. Okay, so when 2s plus 1 is for instance 1, then we call this a singlet, call the term a singlet term. When it's 2, we call it a doublet term. When it's 3, we call it a triplet term, and so forth. All right. Now, how can we now derive the terms for a particular electron configuration of a free ion. Okay, so let's start out with the most simple problem at D2 ion, where we have only 2 electrons to consider that can interact with each other. And you can determine the term symbols for this electron configuration using what is called a microstate table. And you see here the microstate table for this electron configuration. So you see that in this microstate table, the x-axis here is defined by capital ML for the electron configuration, and this axis here is defined by the possible ms values for this electron configuration. So now when you have 2 electrons, you can have 3 possible values for ms. This is -1, 0, and +1. This is because you can have only 3 cases. Okay, one case is in which both electrons are spin up, then plus a half gives +1. The other case is that both electrons are spin down. That explains this -1/2 value. And when one electron is spin up and the other electron is spin down, then that explains this 0 value here. So now, what about capital ML? So now for d electron, each electron can have a ML value varying between -2 and +2. And that means that when we have 2 electrons to consider, the capital ML value can vary between -4 and +4. Okay, so the maximum possible value is 2 + 2, and the most negative value is -2 plus -2. Okay, so the number of microstates now are represented by all the possible combinations of ML and MS value, and you see them now listed in this table. So some combinations are not possible because of the Pauli principle. So for instance, a microstate with an ML value of -4 and MS value of -1 is not possible, okay? Because in this case, both electrons would need to be with the same spin in the same orbital. And that's, of course, not possible according to the Pauli principle. And there are 4 other cases here. For the case of +4, and -1, +4, and +1, and -4 and +1. Okay, but for all the other combinations, there is at least one combination being possible. So you see that for some combinations, there's only one possibility. For instance, for the combination of ML -4 and 0, only one combination is possible in which both electrons have a value of, ML value of -2, which adds up to -4. Yeah? And one electron is spin up, this one here, indicated by a plus, and one electron is spin down. Okay, but there's no other possibility. But for other combinations, there's more than one possibility, and for some combinations, there are actually multiple possibilities. So the most the greatest number of possibilities actually for the combination. Capital ML is equal to 0 and MS is equal to 0. The overall 1, 2, 3, 4, 5 combinations. So the first combination is that the first electron has an ML value of -2, and the second one has an ML value of +2. So -2 plus +2, well, that gives 0. Okay, explaining that 0. And well, one electron is spin up, and the other electron is, and the second electron is spin down. Okay, then you can have also the combination that, well, one electron has the ML value of -2, the other one has the ML value of +2, but the first electron is spin up and the second electron is spin down. Okay. Another possibility is that one electron has the ML value of +1 and the other one has the value of -1. Okay, -1 plus +1 also gives 0. And again, the other possibility that the first electron is spin down and the second electron is spin up, or the first electron is spin up and the second electron is spin down. So last but not least, we can have the combination that both electrons are in the orbital associated with ML equal to 0. That would actually be the DZ square orbital. Then it is required that one electron is spin down and the other electron is spin up. Okay, so we do not need to go systematically through all the many microstates that are possible. I'm just illustrating a few so that you understand the concept. So now, how do we derive the possible terms from this microstate table? So we can do this by drawing systematically boxes into that table. So we start out with the largest possible box that contains the largest possible number of microstates. It's the largest possible number of microstates. Sorry for that. So now this box is defined by, I forgot to say that overall there are, in this case, 45 microstates possible. That is because we have, well, 2 times 4 plus 1 times 2 times 1 plus 1 equal to 45 microstates, according to the formula 2L plus 1 times 2S plus 1, representing the number of microstates. So in general, for a DN electron configuration, the number of microstates is given by this formula here. But now to the question, how do we derive the terms? So we can...
Can I ask a question real quick? Sorry. Is that a general expression you just showed for the number of microstates? Is that just the binomial distribution? Only you applied to the DN, the D case, like you already inserted the n is 10, where you have the factorial at the bottom there? There's like a binomial, like the binomial expression n choose k, if you know what that is, where you have like n factorial divided by k factorial times the quantity n minus k factorial.
You may be right about this.
Yeah, I think this is a binomial distribution.
Yeah, that's probably the explanation for this formula, because of course this formula is just derived from statistics, right?
Oh, totally. Then that's it.
From the statistical way how you can
count the number of microstates.
Count the number of microstates, which is different for each number of electrons.
Right. Cool. All right. Thank you.
In the d orbital. Yeah. Very good comment. Thank you. Okay. So now let's determine really the number of possible terms. So here is again the microstate table, and you see it here in a somewhat more simple form, in which basically each microstate is just represented by an X. Now you see these X's have different colors, and that is because the colors are associated with certain boxes. Okay, and the first box is this one, which is also the red color, and that's basically the largest possible box that we can draw into the table that contains at least one microstate. Okay, now we can look for the microstate inside of the box that has the highest possible capital ML value and the highest possible capital MS value, because these values will determine the term symbol. Okay, so in this case, our term is a 3F term. That is because this microstate here is the one with the highest possible capital ML and the highest possible capital MS. In this case, this is +3 and +1 respectively. Okay, so a capital ML value of +3 determines an L value of +3, which determines an F term. And when my MS value is +1, then my capital S value is also +1, and then 2S + 1, that gives 2 times 1 + 1, that gives 3. So my term is a 3F term. Okay, and in this 3F term, we have 21 microstates, which can be easily seen from this box, because in this direction here, we have 7 microstates, 1, 2, 3, 4, 5, 6, 7. And in the other direction, we have 3 microstates, and 7 times 3, that gives 21 microstates. Okay, so next we can try to draw the next largest possible box. This is actually this one here. So in this box, we find actually 9 microstates, okay, which we have previously not considered. So now again, the microstate with the highest capital MS and the highest capital ML values determines the term symbol. So you see that in this case, this is this one here, okay, because capital ML is +4, and we have here only one microstate, which is associated with a capital MS value of 0. So for that reason, this is a 1G term. Okay, that is because an L value of +4 is associated with the term symbol G, and well, 2S + 1, that is in this case 1, because we have 0. 2 times 0 gives 0, + 1 is equal to 1. So this means that this term here is a 1G term. Okay, so now what other boxes can we draw using the microstates that we haven't considered yet? And the next box that we can draw also contains 9 microstates, and it's actually this box here, the green box, and you see the 9 associated microstates here in them. So what is the term symbol? Let's look at the term that has the greatest ML value. So that's in this case +1. So which is the greatest MS value of these 3 that we can consider? Well, this must be this one here, because this one has the highest value of +1. The 2 other ones would have the values 0 and -1. Okay. So that means that we have a 3p term. Why is it a p term? Because capital ML equal to +1 and the associated L value being also +1 refers to a p term. And when ms is equal to +1 and capital S is also equal to +1, then 2s plus 1 is again 3. So again, we have here a triplet term. Okay, now do we still have any states that we didn't consider? And there's actually, now these 5 here, okay, in this box, which define 1D term. Why is the 1D term? Because within this purple box, the state with the highest ML is actually this state. And with regard to MS, we only have one choice, which is choosing MS being equal to 0. So ML equal to 2 refers to a D term, and 2 times 0 plus 1 is equal to 1 defines a singlet term. So therefore, this is a singlet D term or 1D term. So is there anything left? Well, you see that we have here this black one left. Okay. So there's another term which now contains really only one microstate. And that term is in this case a 1s term. It's 1s because, well, ML is equal to 0. That defines the S. And MS is equal to 0. And that defines that it's a singlet state because, again, 0 times 1 plus 1, that is just 1. All right, now I see we're already 2 minutes over the time. So I think we can just stop at this point. We can stop the recording.